Okay, in this video, you're going to see a couple Greek letters. You're going to see some numbers flying around. Try to not panic too much. There is one small type of calculation you need to do, but we'll also be introducing a tool to do most of the calculations. What you really need to understand here is the concept of what's going on with normal distributions. So this is called the empirical rule, or sometimes the 68, 95, 99.7 rule. Notice that this symbol mu, it's a Greek symbol mu, which is the Greek letter M, standing for mean. Mean begins with the letter M. And this is sigma, lowercase sigma in the Greek, which is the letter S in Greek. It stands for standard deviation. So remember, mean is where something's centered. Standard deviation is how spread out it is. And with a normal distribution, we can really get a handle on where the data are located. So if you look here, what this rule means is if you have data that's normally distributed, so it could be heights of adult females in the US, or SAT test scores, or holding breath times, whatever it may be, if we are going to assume that it's roughly normally distributed, then we can say that 68% of the data, a little over two-thirds, about two-thirds of the data is right here in the middle of the distribution. In other words, it's somewhere within one standard deviation of the mean. And we'll look at an example in just a second. And then if you go out to two standard deviations, so whatever your standard deviation is, if you go out two of those in each direction, you're going to catch 95%, roughly 95% of the data. And then if you go out three standard deviations, you're going to catch virtually all of the data, 99.7%. Still going to be a tiny little bit potentially hanging out in the tails, but it's really rare to get that data. Most of the data is in one standard deviation, and then almost all is in two, and really almost all is in three. So that's a lot of theory. Let's go on to the next page. Let's say you're a college admissions advisor, and you're trying to figure out, you have these two students, you're going back and forth, you only have a position for one, and they're pretty equal in all social activities, all that, and all you have in terms of a difference is one got a 20 on the SAT and one got a 900 on the SAT. Now the ACT and SAT are measured on different scales. They're both normally distributed, but they're different scales. So how do we tell which of these is actually better? First of all, we get a bit more info. So we find out that the average score on the ACT is a 21, the mean, and the standard deviation, it's spread out as a 5. For the SAT, the average is 1,000, and the standard deviation is 200. So notice both of them are a little below average. So still, we're not in a position where we can really tell which score is better. And we do want to assume that the scores on both follow a normal distribution, which they do. Okay, so let's take a look at a visual. I think visuals are very, very important when it comes to normal distributions. So when we say our mean is right here and the mean is 21, we can actually plot it there. See how I've plotted 21 as the mean of the data, the center point. And then when I say we go to the left and right one standard deviation, that literally means we take whatever the standard deviation value is, 5 in this case, and we subtract 5 from 21 to go down to 16. We add 5 to 21 to go up to 26. So between 16 and 26, we can say that roughly 68% of the ACT scores will be between 16 and 26. And then if we would go another standard deviation in each direction, we could say 95% of the scores will be between 11 and 31, and so on. And the perfect score on the ACT is 36. So it gets chopped off just a little bit at the end, but it essentially follows a normal distribution. Same thing for the SAT. Our mean is 1,000, so that's right there in the center of the distribution. And then we go out by whatever the standard deviation. Now it's not 5. For this distribution, it's 200. So we're going to subtract 200 and add 200. And then we can say that 68% of the data 68% of the SAT scores here are between 800 and 1200, and so on. So next, we take a look at the question. So 20 on the ACT, 900 on the SAT, and we try to position where it actually falls in its own normal distribution. So here, if we know that the mean is a score of 21 and one standard deviation down is 16, a score of 20 is in between those two scores, but much closer to the 21. So somewhere-ish around just a little left of the 21. The SAT, on the other hand, 900, it's going to be in between the 800 and 1000, and it should be about halfway in between there. 900 would be halfway in between the 800 and 1000. So now what we can do is we plot both of the points on the same distribution. So instead of having two separate normal distributions, we kind of combine them into the one. And remember, the ACT score was just a smidgen below the mean, whereas the SAT was halfway between the mean and one standard deviation down. So when you put it on the same distribution, you can suddenly see, okay, well, that ACT score, even though 20 is a lot lower than 900, relative to the other test takers, 20 on the ACT looks like it's a little better than the 900 on an SAT. Okay, but it feels a little bit, wishy-washy. So the question is, could we answer this in a better way, a more precise way? And of course the answer is yes. It's all about standard normal distribution. So this is where we take any normal distribution, no matter what the mean is, what the standard deviation is. Those two, by the way, are the address of any normal distribution. If I have a mean of 50 and a standard deviation of 20, that gives me a specific normal distribution that no other normal distribution has. But I can take any normal distribution and convert it to what we call the standard normal, which is essentially they chose the easiest values possible for the mean and standard deviation. They said, well, probably the best mean would be right at 0. That way the positive half is a mirror of the negative half. And then a standard deviation of 1 is about as clean as you can get. You can't get a standard deviation of 0 because then every data point would be right on the center and there would be no spread. But if you have to have a standard deviation, 1's about the best number you can have. So the idea is we want to take any normal distribution and convert it to standard normal. This is also called the Z-score distribution. You may have heard of Z-scores before. That's what we're going to be looking at next. So a Z-score, really what you're doing is you're taking any score and you're seeing how far away from the mean it is. Remember, mu is the mean. So you're just doing a subtraction there. And then you're dividing by the standard deviation. And I'll give you this formula on the test, but I think understanding what's going on here is important. So you're just saying, how far away am I from the mean in terms of standard deviation? How many standard deviations am I above the mean? If it's a positive number, it's above the mean. A negative number would be that many standard deviations below the mean. So that first Z-score we saw, that ACT score of 20, would have a Z-score of -0.2, which would mean it's 0.2 standard deviations below the mean, whereas the 900 was a -0.5, means it's half of a standard deviation below the mean. Negatives are a bad thing here, so this number right here is even lower. The -0.5 is lower than the -0.2. So just as we said, the ACT score was better, but now we have a more precise way of categorizing how close it was. And this is called, again, the Z-score is called sometimes a standardized score because it comes from the standard normal distribution. So when you see some kind of set of educational test scores or business scores or whatever the case, if it says standardized, this is typically what it means. You can do it with other distributions, but typically it's talking about the standard normal distribution. So again, that formula, you take the raw score itself, subtract the mean, and then divide by the standard deviation. So This was from a previous student. They were wondering, like, does Z-scores really show up? And they show up all over the place. But to give you one example, in figure skating or gymnastics, for that matter, um, the athletes don't always do the same difficulty level of routine. They may do a triple sow cow or triple axel or whatever, a triple jump, whereas another one might only do a couple doubles, and the triple's a lot harder. So some of the routines are very hard and some of the routines are very easy. So somehow we want to reward the skaters who are doing harder routines, right? And Z-scores is essentially the same idea as standardizing these scores so that you're not comparing a a skater to a skater doing a difficult routine to one doing a very easy routine. That there's a way of adjusting for that so that basically you can compare two separate scales onto the same scale. That's what the Z-score does. That's what the power of the Z-score is. Okay, let's just do a couple practice questions here. So how many standard deviations above the mean? Right there, that's another way of saying Z-score. Standard deviations above the mean is a way of saying Z-score. Would a student's ACT score of 25 be, given that, just like before, the mean is 21, the standard deviation is 5? If you want to go ahead and try to pause that, remember it's the raw score minus the mean, and then divide that whole thing by the standard deviation. Pause it and give it a try yourself. And this is what you should end up with. So we have that formula right here. We plug in the raw score of 25, mean of 21, and we'd end up with 0.8. In other words, this student was 0.8 standard deviations above the mean, was almost one standard deviation above the mean. Is that good? Well, anything above the mean is probably good. You typically, we might say that 2 or more standard deviations above the mean is really rare or special, or 2 standard deviations below the mean, but it really depends on the context. So then we have a SAT score of 1100. We have this, by the way, the N means normal distribution. The first number is our mean, and the second number is our standard deviation. Go ahead and try that one out. Pause it. Okay, and you should have the raw score of 1100 minus, again, the first number here is the mean, second number is standard deviation, and so we'd get a 0.5. Again, this ACT score was better than this SAT score because it was more standard deviations above the mean. This was only half a standard deviation above, this was 0.8 standard deviations above. So ACT score is better. We can combine it to a single scale and say that this ACT score